Okay, so today we'll finish semantics of first-order logic and try to start the next topic, which is answer set programming. So just recall what we have done last time. So unlike in propositional logic, the notion of interpretation become more complicated because the atomic formula is more sophisticated than before. So it contains objects, the individuals, and also the relations between the individuals. So you have to express those kind of concepts in first-order logic. So we had studied the syntax of formula, which is constructed from the terms and atomic formulas in a recursive way. So here the interpretation is simply giving the meaning to unassigned constants. So here we start with the universe, which is denoted by this symbol. Okay. So when you have I as an interpretation, this I bar represent the universe or the domain of the interpretation. So basically the domain means what are the individuals that can be found from. So which is the set of the individuals that you want to consider. It could be a set of people, set of numbers, or a set of some other things. Okay, so you have to specify what are the domain of your discourse. Otherwise, when you use variables, it's ambiguous. We don't know which what is the objects that this variable ranges over. Okay. Now, when you have object constant, this is to denote a single individual. So the interpretation gives us what is that particular individual. So here we use the symbol C superscript I. C is an object constant. When you apply the superscript I, that means this is now a function that maps constants into an individual. So most of the time, the constants and the elements in the universe can be the same, but there are sometimes it could be different. So if you recall the class discussion problem, there was actually number 10, which was represented by A as an object constant. So there, the A was mapped into, actually here is an example, so A was mapped into 10. Note here that A is a part of the syntax, is an object constant. 10 is not a part of the syntax, it's a part of the semantics. Okay, it's an element in the universe. So something that you might get confused is what is this, where this symbol belongs to. Is it part of the syntax, is it part of formula, or is it a part of semantics? Okay, in first-order logic, A can mean many different things depending on which interpretation that you apply. So this particular interpretation that you saw had A maps to 10, but somebody else say, hey, for A I would map into 11. That doesn't matter. Okay, there are actually many different ways that you can map those individuals. So interpretation just give one particular way to understand this object constant. Same way, if you have a function constant, okay, so this now function constants work similar to the object constant except that it has argument. So it receives some terms as an input and outputs another individual. Okay, so for instance, if we have the successor function, it receives some elements from the universe and it returns another element. Okay, it could be actually the same element too. For this particular one, it was returning the next element, successor function. Okay, all right. Now that is about the term, and what about the propositional and predicate constants? So propositional constant is a special case of predicate constants where there is no argument. So this works very similar to atom in propositional logic. So it's either true or false. So interpretation here will tell us whether this particular propositional constant is either true or false. Okay. Now what about predicate constant? So this is also doing the same thing as propositional constants in the sense that it maps into true or false. The difference is it may contain argument. Okay, so here we have two predicate constants. One is unary, another is binary. So the unary one was receiving one element from the universe, and it was returning either true or false, depending on whether this is a prime or not. Same for Q. If m is less than, first argument is less than n, then it returns true. Now again, here note that Q is an object constant. I'm sorry, Q is a predicate constant. It's a part of the syntax, but when you apply Q superscript I, this is part of the semantics. This is the function that makes us to understand when given the arguments of m and n, whether this returns true or false. Okay? Yes?
So when we talk about a set of functions like gamma, that would map to the which of these cases?
Set of functions is still a function, right? I mean, I'm sorry. Set of function is basically a function of these things, right?
Okay.
Yeah. Okay. So it could be have many other functions. Maybe you were referring to maybe a function that has two arguments. Okay. So addition is another function that you can say. So add. This is not a part of the problem that we saw before, but you can actually define add function as something like this. Okay, assuming that add is a part of the syntax. Okay, are we clear? Okay, so next one. So again, this was what we left over last time. Now, when you have some term a, here a is an object constant, then of course a superscript I is already given in the interpretation in the previous slide. But now, what about the function terms? So when you evaluate this, so in the previous slide we were given how to understand f superscript I. But what in the formula you have f of t1 through tn, where t1 through tn are other terms, right? So how do you evaluate these complex terms in a recursive way? So basically you do the evaluation for the inside. So each of the ti's will be evaluated under this interpretation. And when each of them are evaluated, they will return individuals in the universe. Okay, now you have individuals in the universe as input, then this function f superscript I look at those individuals or set of individuals and returns another member. Okay, so that's how you do. And which member is returned is specified by f superscript I. Okay, so this was the thing. Now that's fine. So we are given interpretation. We know how to understand interpretation, how to evaluate terms, but now how do we evaluate formulas? So here is our way to go. So truth value of f. So formula here is a sentence actually, is a formula that has no free variables. Okay, let's assume that. Because if we have free variables, we cannot actually define. Okay. So we want to evaluate a formula that has no free variables, and we apply the interpretation I. So how do we define it? The first four clauses are very similar to propositional logic, except actually the second, third, fourth are exactly the same things. The first thing is also similar, but because now we have the atomic formula to be more complex. So here, predicate constant followed by the T1 through Tn. So this is the atomic unit of the formula. Okay, the evaluation is actually similar to the terms. So you evaluate each of the terms and then apply the predicate function r superscript I. Okay, so this will either return true or false given this interpretation. So atomic unit will either return a true or false, and those bottom and top are evaluated the same. If you have negation, then of course you flip the values inside of this f. And binary connectives are also the same. Because eventually, these formulas will return either true or false. Now, the new component is about the quantification. So for all w, f of w. So here I use w as an insight, which is to represent that w is a free variable. Okay? Okay. Now we have for all quantification, so then there is no free variable. Okay? So basically what it means is that we want to say this for all w, f of w is true means for all object constancy, when you plug in the object constant, then this formula will always evaluate to true. Similarly, for existential quantification, if you can find at least one object constant that makes fc superscript I, the evaluation of fc under I is true, then we can say this existential sentence is true. And I give you a hint here that this is actually not exactly what we want. So let's think about that. What will be an issue here. So let's try to evaluate this formula now. Okay, exists x, q, x, a, I. So let's recall the same interpretation that we looked at before. Okay, so according to the definition that we are given, so here instead of w we have x, right? So x is actually the variable that we quantify over. Okay, so if this is supposed to be true, according to the definition, that means there is some object constant. So some object constant c, okay, some c, such that f c I equals true. Actually, let me write f c as q c a I equals true. Okay, so I'm just unfolding the definition. Are we together? Okay, now what is the problem then?
For all A.
Huh?
So we have to add for all A that we can.
Well, there is no for all a here. A is an object constant, so we don't quantify over a. A is object constant that maps to 10, so that's okay. Yes.
We need to apply the interpretation I across the function. I don't know if that's the right way to say it, because
Mhm.
our function is q of I, where this is q. C
Oh,
of A.
okay. I meant this one is actually recursively going inside as a first clause. So I wrote in the
Oh.
left hand notation, but as if you want to be fully writing it, I should write it as this way. So that's actually evaluation that is shown. But these are actually the same thing. Okay? So what is the problem here?
Arity of x.
Hmm?
Arity of x.
Arity of x? Well, x is a variable, it doesn't have arity. Arity is only for the function and primitive function.
It's not true for all C.
Not true for all C.
Some C.
So what is the intuition about this formula? If this x, q, x, a, this formula means what? There is some x that is less than 10. Are there any number that is less than 10? Yeah, so this is supposed to be true, right? Is it? How many object constants do we have?
Infinite.
Object constant.
E. Just one. C only.
Okay. The signature was A, P, Q. Okay? The interpretation is only about the signature. Okay? How many object constants do we have? Only one, which is A. So this sentence is same as Q A I or Q A I equals true. Okay? The whole thing that we said about there exist some object constants that maps Q C A C comma A to be true, the same as Q A comma A must be true under this interpretation. But it cannot be true because A cannot be smaller than A. 10 is not smaller than 10. So what is the problem? The problem is there are actually many numbers, but we have only limited set of object constants that cannot name all the individuals in the universe. And that is actually true for first order logic. You don't necessarily have the infinite number of object constants. You may, but not always. Okay? Are we together? Okay, so this is a buggy definition. If you want to say for some object constants this must be true when you plug in, this does not work. Question?
So x here is belongs to n, right? Like it can be.
X is a variable. X does not belong to
So if we
universe.
define-
No, it's not. X is a variable that can range over the elements in the universe, but X itself is a variable. You don't say X belongs to the universe. What belongs to the universe is exactly the set of non-negative integers. X is not a non-negative integer. Syntactically, they are not the same. David?
This last part here, the very bottom line you wrote, is that saying if C is equal to A?
Yes, because you can only choose one C. So here C was a generic name for any object constants. So if you can find some object constant, when you plug it, then this formula must evaluate true. Some object constant C. Now, in this particular example, we have only one object constant, which is A. So I plug in A in place of C.
And so that's saying that it's actually false?
It is supposed to be true. The meaning of this original formula is supposed to be true. But when you write this way, Qi A comma A, what does it mean? This means that 10 should be less than 10 according to this interpretation. Qi returns true when the first argument is less than the second argument. However, for A comma A, you can never satisfy that condition. So it has to evaluate to false, which is actually wrong. Our intuition says that this must be true, but the way that we defined just now doesn't work that way. So this is a buggy. Question?
He ended up choosing A just because it's the only object.
It's the only object constant, according to this buggy definition.
But if he had more object constants,
That's something that we are going to look at later. Okay? Are we together? Okay. This is the part that the formal semantics become rigorous. Some of you already know this meaning as 4 numbers, blah blah, but actually in the formal definition that is not very precise. Okay? So let's look at this way. So what the problem was, we cannot actually plug in all the individuals into the formula. The variable was supposed to range over all individuals, but if we just use only the limited set of object constants, they cannot map to all members in the universe. Because object constants, once you've specified the interpretation, it can map to only one individual. Right? Okay, so the second approach here is, let's say, instead of object constants, the change is actually here for all members of the universe. Okay? So when you plug in all the members, then this must be true. Okay, so for instance, if you have the same example as before, QXA, here what I'm going to do is, this is true if and only if for some member. Q, C, comma A, I equals true. Now, this sentence is actually true, right? Because you can find, this is true because you can find any member that is less than 10. Let's take C equals 9. Then Q, 9, comma A, I is true, right? 9 is less than 10, so this must be true. Okay? Are we together?
Can we see them side by side to see the difference?
Okay. So the difference here was when we have object constant versus member of the universe. Member of the universe. Now the member of the universe ranges over all the members in the set of non-negative integers. Okay? Yes.
So is I always the set of non-negative integers? Is it
No, not
fixed?
necessarily. No. I is an interpretation. How many interpretations can you define? Infinitely many. I can actually map I to range over many different kinds, as well as A can map to 10 or 11 or 12. I can do that. It's actually free, according to the first of the logic semantics. I can do that. So actually, there are infinitely many interpretations I can define, even with these 3 symbols in the signature. Unlike in propositional logic, if you have only n atoms in propositional logic, 2 to the power of n, only numbers can be defined as an interpretation, right? 2 to n is a large number, but still is a finite number. But in the case of first of the logic, the number of interpretations that you can associate with the formula is actually infinite. This is still buggy. It's better than before, but still buggy. Anyone knows why? This is actually more tricky than the previous one. Still buggy. This is where actually the undergraduate logic course stops. Okay, you don't have to know more than this. But since you're in the graduate level, maybe this is good to know.
So what if the I doesn't contain enough members?
I is already fixed here,
Okay.
right? So the question is, even with particular I that we are given like this, there's still something wrong. And yeah.
When you're asking, you mean like if the set of I was an empty set? Is that what you're trying to say?
No, well, set of I. Okay, here I'm not changing I. I is actually
Yeah.
just one.
Okay.
Okay, you don't have to change I. Okay, if you change the I, then you also change everything here. So there's a totally different meaning that we're talking about. So let's not go into that yet.
The members should belong to the signature, not
Okay, can you say it again?
the members which you define there
Ah,
are supposed
very
to
good.
actually only define.
Very good. Do you get it? 9 is another part of the signature. What is wrong here? I wrote Q9, A, and I pretend this as a formula. This is not a formula, according to this signature. Why? Because 9 is not a part of the signature. I cannot use that. Note here that once you're given the signature, you can only use those symbols in the signature to form the formula. How many formulas that you can write using this signature? Again, infinitely many. You can write. However, you are not supposed to use other symbols than in the signature. The only other symbols that you're allowed to use are the like object variables, quantifiers, comma, and parentheses, and equality. Okay, those are just universal for first order logic you can use because they have very fixed meaning. Okay, but the interpretations are only about those symbols that people may define it differently. Okay? Now 9 was not a part of the signature, so writing this way from the beginning is actually wrong. It's almost correct in terms of syntax, semantics, but it's wrong in terms of semantics. I'm sorry, it's almost right in terms of semantics, but syntactically this is not even a valid formula. Okay. The way that we fix is this. So only when you define the meaning of the formula, we are going to extend the signature so that this signature may contain all the names of the individuals in the universe. Okay? Now note here that this is actually somewhat tricky. This extended signature, which is denoted by sigma superscript I, this is not available for domain axiomatizer or knowledge engineer. They cannot use it, okay, because that's not the given vocabulary. Which means that they cannot write a formula using any symbols in this extended signature. They can still write the formulas according to the original signature, okay, but they cannot write any symbols. Here, what we are going to do is we will, the problem is the previous one, just the one before was, we don't have enough name for the individuals. So let's try to create names for all individuals. And these special names will be only used when you define the semantics. Okay? And these will be called object names. Syntactically, they are same as object constant, but we'll call it object names. So let's actually look at the examples. So what I mean by that is n is a set of non-negative integers. So it is actually like this. Okay? We cannot use numbers in the universe directly into the formula, but let's create names for that. So this extended signature will contain all the symbols in the original signature. Okay, let me write this way. This contains all the original signature plus named for all individuals. So instead of 0, I will now call 0 star, which is actually an object constant in the extended signature. Okay? And instead of Q9, A, what I can do now is Q9 star, A. It's possible under this extended signature because 9 star belongs to the extended signature. Then the problem solved. Okay? Now note here that there is certain redundancy because among these things are actually 10 star, right? 10 star maps to 10. A also maps to 10. So there are actually 2 names for the same object, but that does not matter. As long as we have names for all the individuals in the universe, we are done. Yes?
If we do this, then we didn't need to change the definition by replacing for all objects.
We'll see the definition in the next slide. So just wait for one slide. Yeah, that's exactly the reason that we do this. So yeah, so let's just go there directly. So what we do is, this is almost like the last failed attempt, but there we actually use the individuals directly. But now what we do is the names of the individual. Okay? And this is okay now because this formula will be, this psi star, which is the name for the psi, will be only used to define the semantics. Okay? So going back to the previous one, this is not true according to this definition. Okay? If you are confused about all the buggy definition, you can forget it. But this is actually something that you have to remember. So note here that our signature, when we define the signature, when you define the semantics, now we are using this extended signature. Okay? All the names of the individuals here. Okay? So this is now true if and only if Q, okay, Q psi star A I is true for some psi in the universe. Universe is a set of non-negative integers. Okay?
Just one of
Hmm?
If you find only in the text it says if.
Yeah, you can find only one because it's for some, right? Okay. But before we go into that, are we together here until? I'm just copying the definition. Okay. Paraphrase it. So this one is true. Instead of x, if you can find some individual in the universe and put the names of the individuals into the formula, and if that formula evaluates true, then we can say this existential quantification or existentially quantified sentence is true. And yes, you can find anything. This is actually true. You can easily check because I can take psi to be 9. Then I can evaluate Q psi star, I'm sorry, Q9 star. Let me write Q9 star A is true because this is same as Qi 9 star I AI. And this is Qi. 9 star is always mapped to 9. So this is 9. And A is mapped to 10 according to this definition that we have. And we know that 9 is less than 10. So this is true. Okay? So this is a bit too technical for you because humans use intuition to do this. But if you just type the previous definition into the computer, then the computer will just complain that this is a syntax error. And most of the time when you debug, the first thing that you encounter is the syntax error, right? Okay, problem solved. Yes?
So, one question. So basically, the signature that we had, which engineers allowed to use while creating the formula. So why don't we allow them to use
Because.
excellent signature?
Because the formula, when you're given the formula, that's actually a very important thing. You are not necessarily having only one interpretation associated with it. We'll see. We can, why we cannot do? Actually, let me just introduce terminology first and we'll get back to that. So the notion of satisfiability and tautology and equivalence is exactly the same once you understand the truth value of the formula according to the previous slide. So we say that I satisfies a sentence F because we don't want to have a formula without, we don't want to talk about formulas with free variables. So those are called sentence. So I satisfies a sentence F, or also called I is a model of F, if F is evaluated true under that interpretation. Okay? Now, sentence is logically valid if all interpretations satisfies the formula. And two sentences are equivalent if they are satisfied by the same interpretations. If you have free variables, this is just a convention, then you will understand this as a universal closure where all the universal quantification is prepended to the formula. If that is logically valid, we say a formula with free variables is also logically valid. And F and G are equivalent to each other if F is equivalent to G as a formula is logically valid. What you see is was exactly the same thing that you saw in the previous propositional logic. The difference is, of course, interpretations are much richer than before, but that's all hidden in this slide. Okay? So the question was, why don't we use extended signature all the time? The problem is, when you say this is a logically valid formula, okay, how many extended signature that we have to apply? What is given to the knowledge engineer? They can only work with one interpretation at a time. If I say for Lec6, let's actually use a simple one. This formula, is this a tautology?
Yes.
It's a tautology, okay? No matter what interpretation that you apply, this must be true. So which extended signature do we have to use? Which one? Is it okay to use one extended signature to check this? The question is, if this is logically valid, or is it a tautology, then it should be true for no matter what interpretation that you apply. Then the knowledge engineer are given only a limited resource. Okay? You have to specify what you mean by these names. Okay? But here, if you want to say this is a tautology, it actually ranges over all possible interpretations. Okay? Something different here is slightly different. Instead of tautology, for some historic reason, when people talk about first of the logic to be tautology, they use logically valid. Okay, so this is not really significant thing, but there's slightly different terminology that is being actually used in the literature. Okay. Yeah.
So here, so the interpretation satisfies a formula if it will also depend on the universe, right? So
which universe?
So basically, suppose I want to say there exists a root of 3.
When you talk about the logical validity or satisfiability, the particular interpretation is not the point, right? If you can find at least one interpretation that satisfies the formula, then the formula is satisfiable. I don't care about which signature that you use or which interpretation that you use. If you can find at least one interpretation that satisfies the formula, then the formula is satisfiable.
No, what I'm saying is, I want to say whether square root of 2 exists.
Pardon me?
I want to say whether, so there exists a square root of 2.
Okay.
And it will be false.
What is square root?
It will be false if the inverse is integers.
What is the square root? How do you define square root? Again, in first order logic, square root cannot have fixed meaning. Square root is a function, and you can assign any meaning to the function. So when you say square root, you have a particular meaning of square root in your mind, but that's not according to the first order logic. Okay? Actually, we will be heading to that particular argument. What is actually an issue with first order logics? But before we do that, let me finish up some notation. So again, this is same. So set of sentences is satisfiable, okay, if there is an interpretation that satisfies all sentences. And set of sentences entails a formula. You recall the entailment, right? That's one of the homework problem. Okay. Gamma entails F if every interpretation satisfies gamma satisfies the universal clause of F. Okay. All right. So that's okay. But now since let's just do some exercise here. Actually, let's open the Socrative and let's do this. So the question is true or false? So these are the two problems. Okay, so let me go back. So there are two, so you write true or true, false, false, true, false, false. Note here that this is an entailment. All interpretations satisfying the set gamma must satisfy the formula on the right in order for this entailment to hold. Okay. Okay, are we done? Let's see. Okay, so almost there. Okay, so these are the things. False, true, 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 false, true, true, false. Okay, do we see any combination that is not here? I guess every combination is here. Okay, good. Okay, so okay, let's see. So what is the meaning of this thing? So in the first problem, you say basically there is some x that belongs to P, and there's also some x that belongs to Q. Then is there anything that is common for both P and Q? Which is false, right? We note here that I use the same variable x, but don't be deceived by the variable names because bound variable can be always renamed. So when you say exists x px, okay, then x. So let's actually take very simple example. Maybe the universe contains 1 and 2. Okay, so now P is true for 1 and for 2 is false. Okay, and for Q is opposite. Okay. So the first sentence of this formula is saying there is some x that belongs to P. Is it true? Yes. Which one is that x? 1. Okay, so 1 belongs to P, so that's fine. And exists at Qx is also same because 2 belongs to Q, so we are done. So this is the interpretation that satisfies the left-hand side. So for entailment to hold, then this same interpretation should satisfy the one on the right-hand side. Right? Is it? Turns out to be wrong. There is no common element that belongs to both P and Q. So this is actually not entailed. Okay, so checking that it's not entailed is easy if you can find one interpretation that satisfies the left-hand side but not the right-hand side. Okay, what about the next one?
True.
How do you know? Who said true? How do you know?
For all it's,
Everything belongs to P.
it's in or, so anything.
Everything that belongs to P, what? Which P? Which X? Which is universe?
Even if we take the same example here, so it's an or control.
Okay. What's wrong with his argument? Okay, I don't want to threaten, but so you might think that I need to apply this particular interpretation, and so if you do that, what happens to the left-hand side? Huh?
Really false.
Is it false? Then is the entailment true?
It's true.
Okay, there are more steps. Okay, let's go through it. So take this particular interpretation. Does it satisfy left-hand side?
No.
No. Okay, it does not satisfy the left-hand side. Does it? So what happens then? Can we say that entailment holds or not due to this thing? No, right? Why? Because I did only one example, and it happens to make the left-hand side be false. So it does not contradict that this is not entailed, but it does not confirm yet this is entailed, because for the entailment hold, you have to go through all interpretation. So let's choose other combinations. So let's say true, true, false, 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 true, false, false. I mean, for all possible combinations. I did check it, and somehow the this entailment hold for all these interpretation that I tested. Are we done? Do you see what I'm saying? Okay, so let's go back. How many? So you have interpretation. So universe 1 and 2. Let's fix the universe to be 1 and 2. Okay, so that's fixed. How many interpretations are possible for P and Q? 4? Yeah.
16.
How many?
For P we got 4.
Well, for P1 and P2, they can be either true or false. So 2 times 2, and Q is same 2 times 2. So there are 16 interpretations. So those people who said true may have computed 16 possibilities at one time. Good for you. However, that is not sufficient. That is not sufficient. Why? Because you choose only one such universe. How many universes that you can associate? Infinitely many. Did you try infinitely many possibilities? I don't think so. For some reason, still, despite that, you think that this must be true, although you didn't actually verify according to the definition of entailment. In order to use the definition for all interpretations, this entailment should be true, right? This checking must be true. But you didn't do that. Okay, that lies the problem that we encounter in first order logic, undecidability. Let me just finish up this here, and then I'll take the question. So the validity problem is actually a well-known undecidable problem. What is this problem? So you're given a first order sentence, and the question is, can you design a general purpose algorithm or general algorithm? So it's saying, given any such sentence F, if F is tautology or logically valid, the algorithm say yes. If not, algorithm say no. Okay? Note here that this is not only about the validity problem. Okay? You remember how the tautology was related to unsatisfiability and also entailment. That is also part of the homework problem, right? So it's not only this problem, but most of the interesting questions about FOL, like satisfiability problem and equivalence problem, they all go into undecidable problem. Okay? Okay, so if you have time, we can try to prove this, but let's skip the proof in the class. For those who are interested in this, if you go to the computability textbook, there is actually the proof of this. PCP problem can be reduced to validity problem, and PCP is already known to be undecidable. Okay. The corollary here, I told you that since the logical validity is related to other notions in first-order logic, satisfiability problem is also undecidable. Can you find at least one interpretation that satisfies this formula F? This is undecidable. Why? Because you can reduce the validity problem to it, and the main lemma is actually this one. Okay, same as in propositional logic. F is logically valid, or F is a tautology, if and only if not F is unsatisfiable. Okay, so if you can decide this, then you can decide this. Okay, if you can decide unsatisfiability, means you can also decide satisfiability. However, this is not decidable, so you cannot decide satisfiability problem. Okay. So this is actually the problem that we have, and so the lesson here is we have to restrict first-order logic in some meaningful way. Okay? So in propositional logic, the problem was it involves exponential blow-up in the search, right? Maybe that's what we cannot avoid as, for some problem. But when you go into the first-order logic, what we did was simply adding some terms and quantifiers. That's all. And then somehow it becomes undecidable problem. So how can you actually build a knowledge representation language if you have this undecidable property? So you ask the system. Okay? So you can formalize those examples in the natural language problem that we did before. You can turn it into a formula, right? The problem is, even after you convert into a formal language, you cannot answer yes or no for the very basic questions. Okay? Okay, so a question up to this.
Sorry, actually I was trying to say the Lec6 problem, the one that we said false. The first, we had two options, two questions. The follow-up question, entailment question on the previous line.
Okay, so.
Yeah, the first one actually, yeah, if you change the universe for the first one, if I contain only one, this could have been true.
Okay, but we are talking about entailment.
Yes.
Entailment is about all.
All, yes.
Right? So if you can find at least one that does not satisfy, then entailment does not work. Okay? Okay. So we never restrict interpretation that way. So let's consider I containing only one element in the universe. It's not that way. Okay, good. So here's a quiz. Okay, Paul, Quentin, and Robert went fishing. Each caught one fish. There are two fish in total. Okay, what's going on? Huh? Two of them caught the same fish. That was not intention here. Each caught different fish.
Defining total.
Huh?
Like, is total really how we normally perceive total?
No.
They both are the same.
Some of them are actually same person. So Paul and Quentin may be the same person. Of course, this is not the usual way that you write, okay? But if you say Mr. Robinson and Robert and blah blah, sometimes one of the things is actually first name, the other one will be the last name. So if you write this way, maybe not. But if you have a whole corpus, then you will see that the same person can be referred to by different names. So you have to do some entity resolution to see what is what. Okay. Now, why I'm bringing up this is because in first-order logic we have very generous behavior for interpretation. That's actually one of the problems for undecidability. Okay, why is undecidable? Because you have to consider infinitely many interpretations. Okay, So this sentence seems to be a bit weird, but under the first order logic, it is actually possible. This is satisfiable because P and Q may map to the same person. Okay? So often the case, we don't want this behavior. So if you want to use first order logic like a language, we want to restrict that these people are actually different. How do you say that these are all different people in first order logic? So you have to write this formula. For each pair, you have to say they are not the same person. This inequality is actually just an abbreviation. So when you say P is not equal to Q, this is just standing for negation of P equals Q. So this is the equality that you defined before, and it's a negation in front of equality. So if you want to say these individuals all denote different people, then you have to specify this. This is called unique name assumption. So first order logic itself does not have unique name assumption, which means that some individuals can map to the same people. But in many applications, when you do the knowledge representation, you want to say that these are all different. So then, under the first order logic, you have to write this lengthy formula. The general formula is actually here. I'm not going to go into the things, but if you have a terms that has argument, then the unique name assumption is actually this guy. Okay, and actually these two. Okay. There's another thing called domain closure assumption, DCA. So I don't want to consider infinitely many objects. I know, well, let's say the class here, okay, I know there are about 30 students in this class. And I can name all of you, and there's only a limited number of individuals here. So how do you say that all the universe is, I'm going to consider a universe that contains only these individuals. So that's domain closure assumption. So how do you do that? If I want to consider only this, I will write this one. This will be probably very similar to the last question in the homework, right? So for X, X is mapped to either Paul or P or Q or R. It cannot map to other than these individuals. Okay? Are we together? So any formula that satisfies this, okay? Let me ask you, what is the size of the universe whose interpretation satisfies this formula? 3? No? Only this formula. Okay, so take any interpretation that satisfies the formula. The interpretation must have this number of individuals. What is this? 3 is one of the possibility. 2 is also one of the possibility. 1 is also possible. 0 is not possible. Why? Because, as I said before, these people can refer to the same individual. This name, P and Q and R, may refer to the same individual. So most of the time, what you will do is, I will have unique name assumption and also domain closure assumption at the same time. So I can know exactly how many people are in this room and all their names. Okay? All right, writing this in first order logic is a bit tedious to do. So many of the knowledge representation language has some built-in way to express this. Okay, now we are done with this one, and the problem with classical logic. Actually, the root of many AI language is actually classical logic. The problem is, even for the simple propositional logic, it blows up the exponential time to compute. And for the first order logic, okay, it becomes already undecidable. So we have to find a way to restrict this behavior so that it is decidable, also can be computed in a reasonable time. Okay, and there are so much things that is unnatural. Sometimes its unique name assumption is not there. Okay, so things like that. So what we are going to look at is some refined formalism called answer programming. And in fact, this unique name assumption is actually built into many languages, not just answer set programming, but most of the time this guy, actually this guy, this guy, this guy, this guy, all have something. Actually, I would not say this guy because the exception is actually ontology language. If you go to ontology, is this actually possible? Actually, it is more desirable to avoid unique name assumption. Okay, so let's do some introduction to this thing. Okay, so you recall the problem-solving method. Okay, so how do we solve the problem? So we use computer to model this problem, and the output is returned, and from there we get the solution. Now, traditionally, the first part to turn the problem into program is called programming, and you execute, so you get the output, and you interpret this output to get the solution. In the declarative programming that we are going to see, slightly different. So we are going to write something like program, but we call representation, and this is called modeling. And for representation, we don't actually necessarily giving the algorithm to solve. It's not a step-by-step execution. So we call just solving, okay? And it returns output, and we interpret this output to be the solution. So what is this answer set programming? This is one of the declarative programming approach, which is actually widely used these days. The theoretical basis is actually called answer set semantics by Gelfand and Lec6 in 1988. Now, one thing that I want to emphasize here is answer set and stable models that we are going to say, they're interchangeable. Okay? So some books may say answer set, some books may say stable model, they are just the same thing. Okay? There's slight difference in nuance, but that's not relevant for this class. Now, what is missing in first order logic, except for this decidability issue? The first order logic cannot express the idea of default. Normally, this is true. Cannot be expressed in first order logic. Or you can say recursive definition cannot be explained in first order logic. There's aggregate and preference. I prefer this over that. This kind of thing is not expressible in first order logic. Okay, or at least it's hard to represent these things. But these ideas, this kind of concept can be represented as a programming in very natural way. There are actually many ASP solvers available these days, and what we are going to use is actually Klingo, which is actually here. This is the part of the system. Klingo is the software, which is Gringo plus Clasp. Okay, you don't have to know this distinction, but Gringo is kind of preparation. Preprocessor to the Clasp. So we'll just look at it as a package. Okay. There's ASP Core 2, which is a standard language. So if you want to build an ASP solver these days, you have to conform to this standard specification. There's an annual ASP competition that actually makes this solver to be developed further. So in terms of answer set programming, what we are going to do, what you will learn most of the time is the modeling. Okay, so how do you represent problem in terms of some axioms? Okay, and then this part becomes easy. You just call answer set solver, you're done. So the basic idea is you want to represent given problem by a set of rules, and then find answer sets using the answer set, an answer set solver, and extract the solution from the answer set or stable models. Okay, so probably this doesn't make sense to you now, but it will be soon, probably next week. Okay, so there is a n-queens puzzle problem. So the puzzle here is you have to place n-queens in n pi n grid so that no two queens are on the same row, same column, or same diagonal. So for instance, if you have n equals 2, okay, what is the solution for this? You have to place two queens so that no two queens attack each other.
0.
Hmm?
No solution.
There's not possible. Okay, good. What about 3 by 3? You have now placed 3 queens so that no two queens attack each other. Not possible? Okay, let me give you coordinates. So 1, 2, 3 row, 1, 2, 3 column. Okay, where should I put? Someone?
1, 1, 1, 3.
1, 1.
So 2, 3.
2, 3. 3, 2. No, this is not the solution. Okay, I have to erase. Okay. Hey? No. Okay, let me write again. Okay, another try.
No solution.
No solution. Okay. N equals 4. No solution, right? Just one person. Raise hand if you want to try. Yeah. 1, 2. Huh? 2, 4. 3, 1. 4, 3. Is this the only one? No, there's another one which you flip 90 degrees. So there are actually 2 solutions. Okay, good. How about 5? How many solutions will be there if n equals 5? It turns out that there are 10 solutions here. If n equals 6, how many solutions will be there? It turns out actually there are only 4. And n equals 7, now 14. So you will actually do this. Okay, you can easily try and find the all solutions next week. Okay. So the coding for solving this problem, this is the entire program. Okay. If you forget about the comment, the actual program line is 1, 2, 3, 4. 4 lines of the code that you have to write. Now, in order to write these 4 lines, you have to study what is a stable model. Okay. But once you know that, you can write a program and execute this command. So Klingo is the name of the program. You type the queens, which is the name of the file, and -c is actually a placeholder to say n equals 8. So in the previous slide, n was actually not fixed. So you can change it, the parameter. So if you just type in, you will see one solution here. So Q 4,1 means that there is a queen in 4,1, and the similar for the other atoms. It takes a very reasonable amount of time to solve this problem. So this is actually a win-win situation. For solving this problem, you don't have to write a lengthy code. You just write 4 lines, and it can be solved by Klingo very quickly. So you don't have to waste your time for writing a lengthy program. If you want to find all solutions, what you can do is put 0 at the end, and it will return all solutions. When n equals actually 8, which I didn't say before, there are 92 solutions. So it will quickly return, I don't know, this amount of time will be spent for solving this problem. Okay? So it's quite efficient to do. All right, so I guess this is the right time to stop. Any question? Okay, so the next class we will look at the stable model semantics. I linked the lecture note in the class homepage. So it's called sm.pdf, so you can take a look at that. So the materials that I'll present next class will be based on that lecture note. Okay? All right, thank you. So let me open the exit ticket now.